I'm going to give a hybrid talk about hybrid systems. I will use a few slides, and then I'll do some scribbling. And of course, during the slides, you are generally speaking discouraged from talking. That's why we use slides, right? But during the scribbling portions, I encourage feedback as we go. So I will say that a lot of what I'm talking about today really comes out of a problem that arises in quantum computation, and in particularly the prospects of trying to build a quantum computer. And it comes back to, how do I know that I have a quantum computer and not snake oil? And so one wants to understand, how do we test the proverbial or literal black box? And we wanted to understand what properties of a system, what quantum properties of a system we can learn about when we only have limited access to that system. And so I'm going to start by talking about sort of this very specific, what's called verification validation problem. And then after we walk through that, for the second half of the talk, I'll describe our attempts to take the concept of verification and validation and apply it to physical theory. So in other words, replace the black box that's been handed to you by a commercial company with the black box that nature has provided. So I'm going to switch now over to scribbling. And this is your first opportunity to pepper me with any questions. Okay. So let's talk about the black box. Well, we're going to start with a black box that's a quantum simulator black box. And a quantum simulator black box should have a few elements. It has some inputs. You give it some specification of the Hamiltonian. Now, not all Hamiltonians may be allowed. There might be only a small class of Hamiltonians that you're allowed to specify. But there's some specification that you give. You give some specification of the state that you'd like it to start with. Now, maybe you're given no opportunity to specify states. This might be set by the manufacturer, or maybe you have some opportunity to choose a set of states. You give it a set of objects or a set of operators to measure at the end. Now, when I write a measurement set, I actually am generally thinking about what's called a POVM, principal operator valued measurement. And so this means that, for example, M alpha measurement gets a result little m alpha with probability trace m alpha dagger m alpha row. So it's a compact notation, but effectively that's the typical way that we like to write out a real POVM. Technical point. And then finally, I'm also going to give it some time to evolve. Now, how long do I want it to go? In some sense, one of the most interesting things that makes quantum simulators testable is that I can give it a wide variety of times. Right? So it's not just implementing one unitary, it's implementing a whole class of unitaries. And of course, what comes out are the measurement outcomes. So we'd love to be able to validate our system given the choice of inputs and the measurement outcomes that come out. Now, if you like to think a little bit into the further future, not only might you get the measurement outcomes, you might get also the state on the output, so that you could then put that into a quantum Merlin-Arthur type architecture for checking a proof, where the proof is handed to you in the form of a quantum state. But I'm largely going to ignore that here. If someone's willing to build me a quantum computer that hands me the state at the end in the form of some trapped ions or the like, and I can carry it off with me, okay, then that'll be fine. But I anticipate that's going to be some time. So that's the setup for the quantum simulator. And so what we'd like to do is, first of all, be able to test some properties of the black box. And maybe the simplest one to test is to ask whether the black box is using any entanglement at all. So we can compare the distribution, the probability distribution of outcomes m alpha for a quantum evolution, thus this e to the minus I ht, versus classical evolution. Now classical evolution here, I have to define it. I don't mean semi-classical evolution. By classical evolution, in this case, I mean evolution of Schrodinger's equation restricted to product states. So that's an extremely restrictive choice. And so we're not going to learn very much about our black box. But hey, I can make some progress with it, so I'm going to work with it. Yes?
Are you allowing yourself, are you just doing sort of one-shot experiments, or are you allowing things like, say, the swap test, where you compare two sets and then you think that you find the outputs?
Because I'm only looking at measurement outputs, I can't really do the swap test. If I had the copy of the state at the end, I could do the swap test. But at the present time, I'm not allowing myself access to the state. Well, no, I'm getting readouts from the manufacturer of what they claim is measurement output.
Oh, I see. So you just get the data.
I get the data.
You get a piece of paper with
Well, you know, maybe it's not paper, but some classical bits. That's for sure. So the point is that we can run it many times, though. So we can build up probability distributions. So this is not generally going to be single-shot testing.
So you're assuming you trust the manufacturer.
I have to assume some promises, and then given that assumptions, then I can test certain things. So as I go, I'm going to relax some of those assumptions, but I'm starting with the simplest possible thing, which has the most assumptions, and then we'll move back from that a little bit. With respect to the restriction of product states in the classical evolution, you could also put in mixed states. That's not going to fundamentally change the outcome, because essentially that will, but it can obfuscate things, right? So if your goal as a manufacturer is to not obfuscate, to prove you pass the test, then actually mixed states will be a failure for you. So the point is that, and this is, we have kind of come up with a constructive example for this particular set, and this is a collaboration with student Min Tran and Rentu Matthew, where what we've been looking at is an example where we can, using a classical computer, predict the probability distributions for the full quantum system, as well as the probability distributions for the classical system. So then we can compare the two. Now this is in contrast, for example, for Scott's beautiful proposal for boson sampling. Right, boson sampling has a very similar structure, in that you have some probability distribution that comes out, and knowledge of that probability distribution requires, in that case, solving a hard classical problem, we think, with high certainty. Whereas here, we're trying to set up a scenario we want to test, so we need that the quantum distribution is one that we can calculate even classically. And so, as our example case, we chose the central spin problem. So the Hamiltonian is a sum of spins interacting with a central spin. It has some magnetic fields, where Jz is the sum of all spins. Now the central spin Hamiltonian has a long history. Its main benefit is that it's an exactly solvable model. And that allows us to make predictions about its probability distributions. Its secondary main benefit is that even in the presence of disorder and errors in the implementation, I'm going to look at the cases in particular where I have some external magnetic field variations, that even with that term added on, I can still efficiently predict its probability distributions classically, at least in the high field limit. And so this sort of setup, it's a very particular problem. It turns out it's not so peculiar though, because if you're familiar with literature on condensed matter theory, you know that, for example, the BCS Hamiltonian is an example of the central spin problem, where it's a sum of central spin models. And actually, the central spin problem also occurs in physical systems, mostly in spins in semiconductors. And so there's a pretty wide literature on it. It also has a classical integral results, which you can sort of semi-analytically write down. So it has a really fun literature to work with. But from our perspective, its integrability wasn't so crucial. It's just the predictability that matters. And so with that predictability element in mind, we can look at, for example, what happens under quantum versus classical evolution. And what's interesting here is that there's sort of the classical evolution. And this is in the original frame. And the classical evolution is product states only. And the problem here is that I have this one central spin, which is picking up quantum fluctuations from all the other spins, and then trying to pass them back. And if it tries to do that under the semi-classical approximation, the product state ansatz, it just can't. And so I get the classical original frame has a probability distribution, which I'm going to draw like this. If I do the same thing for the quantum case without disorder, I'm going to get actually a very different distribution. And this axis here is the probability of a given value of Jz. But I can also move frames. I can do what's called the Schrieffer-Wolff transformation. You can think of that as a perturbation theory. I have an excitation manifold of low energy excitations of spins down here. Up here, where here the central spin is down, here the central spin is up, and I'm using the assumption that H0 is much larger than all of the energy scales. Then I can essentially do a perturbation theory in which I include a virtual process where I go up and come back down. And I can apply a unitary transformation of my Hamiltonian that removes those virtual processes to some order. That's the Schrieffer-Wolff transformation. So after the Schrieffer-Wolff, I now have a all-to-all coupling Hamiltonian. It looks something like the sum of S plus J, S minus J prime, plus additional terms, and it's over all the spins. And as you know from mean field theory, when you have an all-to-all problem, mean field theory becomes exact in the large n limit. So here, after Schrieffer-Wolff, classical and quantum are in agreement. And so I can run a classical simulation here with this order and then compare it to the quantum case and go back to the quantum case and discover that this sector here predicts one set of distributions, this sector here produces another, and then I can even average these distributions over disorder. And what we can discover is that the Hellstrom distance, the distance between these distributions, goes as 1 minus lambda, where lambda is the strength of the disorder, raised to some polynomial in the number of spins. And the polynomial is roughly n to the 1.5. So what that tells us is that actually even with disorder, we can distinguish these two distributions, which is very nice if you're building a quantum computer and you can't do it perfectly, but you can at least make some confirmation. Oh, I did this test, and even with my disorder, my distribution is still sufficiently distant from the classical distribution. Of course, the loopholes in here are miles wide. And so you could certainly easily defeat this as a measure of your performance. So we'd like to close some of these loopholes and improve the situation. And towards that end, we're going to start asking, well, what if we can get a little bit of quantum information in and out of the system? Right? Not just specifications, which are essentially classically defined, but not just measurement outputs, but also maybe 1 or 2 qubits go in and out. So now it becomes a little bit of a different problem. And the way I like to think about this is I have a qubit 1 and a qubit 2. These are under my control. They interface with the simulator. I can have some evolution in between. And then I make these measurements at the end. So this circuit now allows me to look at some quantum properties of the black box that I wasn't able to get to when I only looked at classical measurement outputs. Now, I'm still not getting the full state out. I still can't do the swap test. But I can test more. And it seems quite reasonable to ask a manufacturer to send out a quantum photon, for example, from your device to test some property, or to send the quantum superposition photons in. Of course, I asked the DWF chief engineer this about 6 years ago, and he said, no way. You win some, you lose some. But the point is that having a small quantum interface is actually already enough to start testing more properties. So what can we do? Well, I'm going to use an example case to illustrate the general point. And the example case is the world's worst quantum simulator. It's a harmonic oscillator. But okay, harmonic oscillators are a great starting point, right? Maybe Yikai would disagree and say the worst case is a single qubit, but I'm going to use a harmonic oscillator because I trained in quantum optics, and that's my love of quantum mechanics comes from harmonic oscillators more than from spins. So let's consider what happens with a harmonic oscillator. What is the protocol I could use to entangle these two qubits to prove that there's some entanglement ability within this system, that it has a non-classical nature? So what I can do is I can apply a series of operations. First, I can displace the harmonic oscillator, by some amount in the x-axis, that is, the sign of which is determined by the spin of the first qubit. So it's a conditional displacement operation. So I'm going to draw the phasor diagram for the harmonic oscillator. Here's x, here's p. This is the initial sort of wave function, if you will, centered around the 0. And then if I either go this way for up, or this way for down, and I have these two new possible values, I produced a small cat state, if you will, between the harmonic oscillator, which is our simulator, and that first qubit. I can evolve. So these things can rotate around because it's a harmonic oscillator. And if I wait a 2 pi period, it comes back to itself. Then I can attempt to remove that excitation using the second qubit. So you see there's 4 different outcomes that can come out of here. Right? I can go twice this way, or back this way, twice this way, or back this way. Now 2 of these outcomes are sort of degenerate. They go back to the same state I started with. 2 of the outcomes are quite different. So let's define those things. So I can look at the case in which they're both up or down. And I would see that I have exponent of minus 2i, or sorry, I should say minus plus 2i eta p. U, where x has been moved to x plus eta, and then whatever the state of the simulator is. So I can have this, and I'm going to define this object here to be a w plus minus. We'll use it again later. So it represents leaving an excitation behind on the harmonic oscillator. The other scenario is up down or down up. And in those scenarios, I have first the the displacement, and then the reverse displacement to remove it. And so I get a unitary of x, or the unitary but where x has been moved to x plus minus eta on psi. This is the key step. If this is not clear to you, speak up now.
The oscillator is the middle thing in your circuit diagram?
The oscillator is the simulator. That's right.
You're not really, you're just simulating a polarization.
So
What is
I don't know how I'm simulating it. I told the manufacturer, turn it on and let it run. Now turn it off, and I'm gonna bring my qubit in.
You want to see if they were doing this with
No, I want to see if I can get entanglement through. I'm not testing whether they actually have a harmonic oscillator. I'm testing whether I can get entanglement through.
Oh, I see. So that doesn't matter what entanglement.
I can certainly not get entanglement if they chose the wrong Hamiltonian or if I didn't understand what I had. But if I do get entanglement, it in some sense is independent of those choices. So let's define this, by the way, as x plus minus, capital X. So you can see that if I make a measurement, say I measure the vacuum or its complement, that's my POVM, and I conditional on this output, then I collapse myself to when I get success to being in this up, down, down, up space. So the initial, say, plus plus state goes to a Bell state. In particular, it goes to this up, down, plus down, up state. So I've generated entanglement, post-selected upon this measurement output. And now, of course, I can test that I have entanglement. We can agree amongst ourselves that if the simulator is purely a classical box, there's going to be no entanglement. And so, in some sense, this allows me to test the capacity of this black box to entangle. What's interesting here is that the entangleability of the black box is actually independent of the protocol so much, because it really just depends on the properties of the state and the simulator's evolution. In particular, you can show with some more effort that if I call this projection P, in general, entangleability arises when the state of the simulator, x dagger minus P, x plus psi s squared, the scenario in which I get the right post-selection result and I remove the excitation from the system, is greater than, actually it has to be strictly greater than for entanglement. Sorry. The scenario in which I measured, or I got rather, including in post-selection, the excitation left behind. So these are properties of the state and of the simulator itself. Not so much the qubits I attached to it. And everything looks really groovy, except you'll notice that this object right here is a bit funny. This is what's called an out-of-time order correlation function. And that's because of that minus sign on the x. It involves propagating forward in time, making the projective measurement, and then propagating backwards in time. And so that looks like it might be hard to actually measure in a physical system. But we have a simple trick for dealing with that, which is you need one qubit. So you don't actually need two qubits to check the entangleability of the system. You do need one, though. And with one qubit, what you do is you apply, starting on S simulator and the qubit in the state plus, you apply X sigma Z. And that produces this state x minus 0, x plus 1. And then if I measure the 0, 1 expectation values via tomography, I can infer this out-of-time order correlation function. So the point here is that I can test the ability of the black box to convey entanglement. And there's some correlation functions that if I measure these correlation functions and they violate this inequality, if they're above this inequality level, then I necessarily can entangle. I don't actually have to violate Bell's inequality to show entangleability. So it's worth mentioning that concept has been used a bit now in optomechanics to show the entangleability in harmonic oscillator systems. But let's move to bigger fish. Now, they say sometimes you have to teach the controversy. So very recently, poor Sabine had the facepalm moment of seeing this comment appear in Nature magazine. This was just a few weeks ago, about testing quantum gravity in the laboratory. Now, for those of you not familiar with it, there is a long history of lots of people trying to figure out how to do this well and making lots of effort, which was all promptly ignored by several recent authors who had a Nature feature article, not a research article, of course. The research article came on the archive a few days later, where they promptly ignored everyone again. But the point is that a good idea is just always keep coming back up, right? And so I would say you really should just understand there's a good idea here. And the good idea is that wouldn't it be nice to learn more about gravity by making a superposition of a mass in two places? And now it comes up to the experimentalists to achieve that goal as well as possible, and up to the theorists to say what it means. So I'm going to do a little bit of both in the remaining 15 minutes here. I also want to mention very recently, this is a paper in the archive from March, was a demonstration of a non-classical massive superposition at the 100 microgram level. So this was done in Robert Sholkoff's group, Yuan Xu is the first author. What they did was they took a transmon type qubit, essentially a two-level system. This is this squid that you see up there. And they built a piezoelectric transducer underneath it, a small thin film, that drives a mode of a thick piece of aluminum, of sapphire, sorry. So this thick piece is, aluminum oxide. This thick piece of aluminum oxide is being driven by the piezo mode that produces a resonance. That resonance is a harmonic oscillator. It corresponds to a mass of about 100 micrograms. And what they can do is they can make, on that corner here, you see they do a 2 pi pulse on the qubit. They make it into superposition of 0 and 1. Then they couple the oscillations of the qubit, which is like a little electrical resonator, with a mechanical resonator. By stark shifting the qubit, they wait some time. They couple again, so they put the excitation into the resonator, they take the excitation out of the resonator. This is a single Fock state, right? A superposition of vacuum and one phonon. And this is what's called Ramsey spectroscopy. So you can see the Ramsey spectroscopy works out. They can actually see coherent oscillations, up to about 80 microseconds. And this is a 6 gigahertz resonator. And it's very interesting. It's very compelling for me. And what I like about this, so you have this quantum Q of about 10 to the 5. It undergoes 10 to the 5 quantum mechanical resonant oscillations before it starts getting decohered at the sort of 100 microgram level. Now, if you look at what's happening to the metric, this little mass is producing a difference in metric at a part in 10 to the 15 by being in these two slightly different places at the same time. To put that in context, if you look at molecular interferometry experiments, like from the group in Vienna, Marcus Arndt's group, where they take a molecular weight of 6,000 molecule and they spread it out over a few hundred nanometers, that makes an imprint on the metric on the order of 10 to the minus 22. Right? So we're really pushing up in the imprint we can make on the metric by orders and orders of magnitude. Now, of course, you want to get to order 1, right? if you want to see high curvature, but of course, we'll have to deal with just much bigger than 10 to the minus 19, right? Which would be sort of the typical LHC type picture, but much less than 1. So, my projection here is that we're going to get from this sort of part in 10 to the 15 difference in metric to part in 10 to the 12 difference in metric over the course of the next 5 to 6 years. And so it's up to us to figure out what we can do with that. From my perspective, what we can test at the simplest level is something that we think gravity is not, which is classical. So what is classical gravity? Well, it comes back to what's a classical force. It's something that acts between two particles, but doesn't entangle them. So classical communication is perfectly fine. Quantum communication is right out. And so you can actually construct, and I'll do it momentarily, kind of a full theory of gravity, which is, you might say, the universe as simulation theory of gravity. It's not very intellectually satisfying because we don't think it's correct, but you can hopefully disprove it. But more to the point, it turns out that this sort of picture of a classical force for gravity emerges in multiple different pictures of what we might mean by a quantum theory of gravity. So the sort of least likely scenarios are what might fall under the sort of Diossi-Penrose theories of spontaneous collapse. And in fact, Diossi back in the 80s started looking at exactly the questions that we're looking at now, trying to understand if you could make spontaneous collapse compatible with quantum mechanics in any way or form. Now, what is spontaneous collapse? Well, it basically corresponds to some statement that gravity is somehow nonlinear quantum mechanics. So that would, of course, be interesting from computational complexity perspective, because, nonlinear quantum mechanics, the door is open. But if we assume that that's probably incorrect, you'd like to somehow make them compatible. And it turns out you can make them compatible by adding some noise. And so it turns out nonlinear quantum mechanics with noise is no more powerful than linear quantum mechanics with the right noise, which is interesting.
Is there a reference for that? Or who shows that?
Well, it's simply a statement that I'll show you momentarily that the nonlinear case is actually an example of a linear case with feedback. Classical feedback.
Okay, well, I mean, there are types of nonlinearities, like just a fundamental decoherence mechanism that wouldn't give you all this computational power.
Yes, but I think actually Newton-Schrodinger does give you computational power, substantial computational power.
All right. But not with noise?
But not with noise.
Okay.
So
I'll be very interested to see what the thing is.
I won't tell you the first half, I'll only tell you the second half. So you have to infer the first half on your own. Yeah.
I thought the thing that the usual sort of straw man to go after when you talk about this, I thought was the idea that gravity is classical and it couples with the expectation value of the energy momentum.
Well, I would say it slightly differently. So in order to have them make any sense, you have to define what that means.
Yeah, so I think it doesn't make much sense.
Well, I'll define an example where it does. But more generally, the point is that it's not just this sort of Diossi-Penrose, which is the easiest to disprove, but it's also the concept of what you might say equation of state gravity. Right, so if you think of gravity as some emergent thermodynamic property, then you might anticipate that it wouldn't have an entanglement capacity. Because as it tried to entangle, it would necessarily scramble too fast. And so you would never be able to get two things entangled without having gravity stuck with it too.
That might just mean it's hard to do.
Well, so we can talk about this after, but the point is that it seems likely that the boundary of equation of state gravity that allows entanglement is essentially zero. So that doesn't mean that you can't make some ground state version of that equation of state gravity, which actually does make sense, but it means the sort of thermodynamic picture of that will be inconsistent with entanglement capacity through gravity. And so you can see when I set it up this way that this concept of testing a black box for its entanglement capacity can also be applied where the black box is gravity between two objects. So I guess the basic concept that I have to really show this in some more detail is to break it up into a small little picture, and then I'll give you the sketch of the general theory, and then I'll conclude. So the basic picture is that if I have two parties, Alice and Bob, trying to communicate, and they have basically a force between them, and we assume that locally quantum mechanics is right for each of them, and that the interactions between them are not non-local, then necessarily there's got to be some carrier of information that's going back and forth. So you can imagine I put a carrier of information going back and forth, and that carrier of information is then going to lead to forces between them. If I add a screen in between them, a purely mathematical object, I can remove the capacity of that particle moving back and forth to convey entanglement. And so we're going to take a sort of adversarial approach. In this case, we'll say, well, let's say there's an adversary trying to prevent entanglement from getting through. Like, what are the properties of that adversary? We require it to reproduce classical dynamics. We call this sometimes the Ehrenfest dynamics, right? And that's a very stringent restriction. You want basically what we expect to happen in our solar system to keep happening. But you at the same time also want to let no entanglement through. And so it turns out that we can use a nice result from Michael Wolff in quantum communication, which essentially says the best adversary for this type of process is the heterodyne adversary, or the heterodyne channel. So let's make this thing make a little bit more sense. So let's define an interaction like G, A, B. That's the interaction that we observe, say, in nature between two masses that are near each other. A represents an operator on system A, B represents an operator on system B. So we can generate that with a force carrier or some other ancillary object, I'll use a harmonic oscillator again, via a sequence taken from ion trap literature in which I apply a displacement of the oscillator by an amount capital A times eta. Then I apply a boost by amount capital B. And then I undisplace and I unboost. So you'll recognize this is a unitary transformation of the middle object. Like this. And A and B commute, and X commutes with X. So the whole thing is just the exponent of minus I eta squared A hat B hat. And via trotterization, you can imagine this as a way to realize e to the I vt. And so this becomes equivalent to some exponent of minus I, some small tau, v. So what do you do? Well, right in the middle here, you insert the screen. And what does the screen do? Essentially, it takes that. So here's your phasor diagram, x and p. You moved over this amount a to a. You moved up this amount a to b. And what you try and do is, as well as possible, measure both x and p. And feed forward those measurement results to the second half of the circuit. So you're replacing the quantum values essentially with classical numbers. Now this is called the heterodyne channel. Yes, go ahead. No, it doesn't destroy entanglement, it just prevents entanglement. It's a little bit different than a firewall. No. No, they can still be entangled by electromagnetism, for example. I'm just excluding this one force carrier, like gravity. That's correct. So anyway, the point is that essentially you measure the x and p of this ancilla, and then you feed forward those results. And so you can actually now build a whole theory of fictitious, if you will, gravity this way, or the universe is a simulator of gravity. And then we hopefully can show that it's not true. But what's nice about this formalism, by the way, is that you can encompass both thermodynamic gravity and this sort of Diossi-Penrose picture under the same overall story and make some self-consistent picture of semi-classical gravity. So what do? Well, I basically say here there's the simulator, which has an estimator, rho s, of the universe. And by the way, I'm assuming this, as Michael did in his talk, some ADM type formulation of space-time, so I have a 3-manifold and another 3-manifold, and I have some short time evolution between them, which I can capture using the dynamics of curved space-time. So I have the simulator, then I have the universe, the actual thing that we think we live in, which I'm going to take to be a pure state. It generalizes, but. Now, from the simulator estimator, I can solve Einstein's equations. I can define g mu nu as 8 pi trace of t mu nu on rho s. So this gives me a metric g. And I have the whole history of rho available to me, right? So it's a simulator, it knows everything. And so given that G, I can define U, say, of T plus delta T, T. That's the thing that goes from here to here. Takes one manifold up a short time in the lapse vector. I'll let little g. So I have this U that I've computed, and I apply it to both systems. The system I'm sort of blind to, the universe we maybe live in, and the system in the simulator. So I have rho s tilde is this UG, rho s, UG dagger, and UG psi is psi tilde. So I evolve a short time step. Then,
Sorry, can you clarify? Are you trying to test, the usual general relativity here? I mean, this is not the equation that we would usually write. Usually we would say that d mu nu is an operator. We write down that equation, and d mu nu is an operator. And Einstein's equation is an operator equation because it has a trace.
oh, here the trace is not over mu nu, it's over the density matrix.
Yeah, that's what I'm rejecting.
Yeah, so here G is a classical number. These are all classical numbers.
Yeah, but I mean, this theory, so this is not quantum mechanics.
The left-hand side is not quantum mechanics. That is correct.
Yeah.
Left-hand side is, essentially what I'm doing is I'm suggesting you can generate a self-consistent metric solving Einstein's equations using estimators produced by weak measurements on an actual system.
But the metric is sitting there inside of t mu nu, right? So you don't even know what the Hamiltonian is until you know what the metric is.
Well, I have made some assumptions. The main one is ADM, and once I've done that, things become a little bit easier.
I think it means that for example, the Hamiltonian is a nonlinear function of the state of the system.
Yes, but it's only nonlinear function of the expectation values of the state of the system,
Yeah, but
which I'm accounting for in the simulator. What's that?
That's not e to the minus I h acting on Hilbert space, right?
Well, U, this thing here, is the Hilbert space evolution on the curved spacetime given by G.
But you don't know G, right? I mean, you have to.
The simulator knows G. It has this classical trajectory that it solved.
Because you have to put the state in, right?
Oh, you're asking how do I bootstrap the state?
Yeah, U depends on the state. Usually in quantum.
Well, okay, so the rho s here, this is classical. This is some classical set of numbers.
Is t mu nu an operator?
T mu nu inside is an operator, after the trace is not, yes.
Okay, so then rho s is not.
I'm saying that I have constructed a simulator theory, right, with exponential resources in order to make the impression that I've got quantum mechanics working for me on the gravity side without actually having it. And I guess the last key point is that there's some weak measurements that have to be applied. You get measurement outcomes m alpha, and given those outcomes, you get that the psi afterwards is proportional to m alpha on psi tilde. And this is where you're getting information from the universe to feed into your simulator. These weak measurements of m alphas. Now, what m alpha do you choose? Probably some distributions of stress energy at various points in the space-time. And you also apply this on rho s tilde to get the new rho s, and then you feed it back in. So what this is doing is this is evolving the actual system over here on a curved space-time with some measurements. But it's a classical curved space-time. There's no quantum curved space-time here at all.
Is gravity dynamical?
Well, gravity is dynamical, but it's being driven on the simulator side. So what this allows you to do is describe a self-consistent semi-classical theory, because at no point do I break linearity. At no point do I have to resolve the question, what do I mean by the expectation value? The expectation value is given by the simulator. Of course, this is testable, right? We expect it to be wrong. How do we test it? Well, we look for excess noise, essentially. So this heterodyne screen introduces a single extra vacua of noise. And so what you can show with not a lot of effort, actually, is that you can, between two coupled mechanical oscillators via gravity, get an extra heating rate if gravity behaves in this way. In general, if gravity doesn't allow entanglement, you get a heating rate of about 1 phonon every 3,000 seconds for typical parameters. Now that's hard to see, right? Because we're dealing against heating rates with the best experiments from the University of Washington group on the order of 1 phonon every 100 seconds. But it's not impossible, or every 10 seconds. In particular, you can kind of run the numbers and see in about 3,000 years with one experiment you can do it. Now we think we can do better by making bigger superpositions. That's an area of active research for us. It's also worth mentioning you just repeat the experiment many, many times. And then I guess I just want to close off with saying that I know this sounds like, okay, so that's really low-hanging fruit in gravity. We probably think it's wrong. Why do we test it? Well, I think if you could show that the heating is not there, what we've proven is that necessitates that gravity has quantum capacity. And we think it does, but how do we show it in the lab? And this is an opportunity to do so. It's worth mentioning that we're now pursuing a collaboration, and this is from Julian Sterling, who is the postdoc building the big G apparatus at NIST, where we're just going to run a little test using this big G apparatus, which is a torsional oscillator system, and see how many orders of magnitude away are we with the current technology. And I'll just close off there. Thanks very much for your time.